Hello. In the previous lecture, we were discussing Cauchy Riemann conditions, and we had derived both the conditions and also the complex form of the complex form of the Cauchy Riemann conditions and the polar form of the Cauchy Riemann conditions. In today's lecture, we are going to see a few more things related to Cauchy Riemann conditions. So I will start by a little bit of revision. So, and then we will proceed. Okay. Okay. So the topic yesterday we were discussing was Cauchy Riemann conditions. Okay. So let us begin by a little bit of a revision first, so that the things that we discussed yesterday gets revised, and then we move to the next topics. Okay. So in summary, yesterday we did this thing that that is, if fz is given by u plus iota v and f is differentiable, then the first thing that we derived was the derivative of f. That you should remember, I think, because at times this is directly asked in the exam, so you remember this thing. Then f dash z can be written as ux plus iota vx, and f dash z can also be written as vy minus iota uy. Apart from this, this u, v satisfy the Cauchy Riemann conditions. That is the partial derivatives of this. The first order partial derivatives of u and v satisfy the celebrated Cauchy Riemann conditions. They satisfy these Cauchy Riemann conditions. Okay. And what are these Cauchy Riemann conditions? The Cauchy Riemann conditions in Cartesian coordinates. In Cartesian coordinates are ux is equals to vy and uy is equals to minus of vx. These are in the Cartesian form. In the complex notation, we know it is given by del f upon del z bar must be 0. And in polar coordinates, we know that this is given by ur is equal to minus 1 upon r v theta, and u theta is equals to minus r here. Okay. So having done all these things, I did a question for you last time. So just look at that question. When we did this for differentiability, we precisely wanted to know whether fz is equal to z bar is differentiable at z equal to 0, and I proved that this is not differentiable at z equal to 0. If you really think u is equal to what? X, and v is equal to what? Minus y. If ux is equal to what? 1. And what is vy? Vy is equal to minus 1. So clearly Cauchy Riemann conditions are not met. Cauchy Riemann conditions are not met. So clearly it is non-differentiable. In fact, it is not nowhere differentiable now. Okay. Earlier we were just trying to find at 0. Now I have proved that the failure of Cauchy Riemann conditions means it is nowhere differentiable. Because for differentiability, the necessary condition is Cauchy Riemann condition. That is, if f is differentiable, then Cauchy Riemann conditions must be met at some point. But clearly, it will be not true for any point. Ux is equal to vy will not be true for any point. So therefore, Cauchy Riemann conditions do not hold true for any point. Okay. Now the question is, otherwise, also you could have seen that del f upon del z bar is equal to what? 1. So clearly, it is not differentiable again, because the necessary condition for function f is equal to u plus iota v to be differentiable at a point is del f upon del z bar should be equal to what? 0. But it is equals to 1, so it is non-differentiable. Really not differentiable. Okay. Now, let us think about another thing, a few other things that we did. Fz is equal to mod z whole square. Sorry, mod z whole square. What do you think about this? So it can conveniently be written as z into z bar. Okay. Now, if it is differentiable, then del f upon del z bar must be equal to what? 0. And it implies what? It implies z must be equal to 0. It implies that this function, which is fz is equals to mod z whole square, is only differentiable at a point z equal to 0. Okay, so z equal to 0 is the only point of differentiability here. I hope it is clear. Okay. So, another thing, let us do another, just think about this particular thing that I'm writing right now. So let us consider any polynomial. Let us consider a polynomial. Let us consider a polynomial. And what this polynomial is, let's say pz is equals to a naught plus a1z plus a2z square plus a3z cube and dash dash enz. Okay, so let us consider that this is polynomial, and let us change this z by z bar. Okay, so I'm replacing z by z bar. So now polynomial becomes simply a naught plus a1 z bar plus a2 z bar whole square plus a3 z bar cube, and at the end an z bar whole raised to 5. So this becomes that polynomial. So z replaced by z bar. Now my question is f is this particular function? This we know it is differentiable everywhere, continuous everywhere. So polynomial function has got no problem. It is continuous and differentiable on finite complex plane. That's not a problem. Now, what about this? Is pz bar differentiable function on entire complex plane? Or what are those conditions? Or under what conditions does it become differentiable? Under what condition pz bar is differentiable? Okay, so let us address this particular uh, thing first. Okay, so if this is differentiable, then we know that pz bar del pz bar divided by del z bar must be equal to what? It must be equal to 0. And it implies what? It implies that a1 plus 2a2 z bar plus 3a3 is z bar whole square dash 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 nan z bar n minus 1 should be equal to what? 0. And we know that all of these are linearly independent. So clearly we can say that A1 should be equal to A2, should be equal to A3, and all these values should become equals to what? 0. If all these things become equal to 0, it implies what? It implies that pz bar must be a constant function equals to A naught. That is, pz bar must be a constant function. So if pz bar is differentiable, it can only be differentiable if it is a constant function. Okay. Okay. Now let us move to another little bit a different direction. Another way of writing Cauchy Riemann conditions. See, uh, at times you may find different variations in exams, so you have to remember all of these, or probably you should keep in mind all of these. Another form. See, another form can be the same form that is in U and V. I can write in F also. So if Fz is equals to U plus iota V is differentiable. Is differentiable at Z naught, then CR conditions can also be written as let's say can also be written as iota partial derivative of f with respect to x at x naught comma y naught equals to fy at x naught comma y naught, or simply iota fx at z naught should be equals to what? Fy at z naught. I mean, I have done all these things, but just to remind you that this is another way of writing the Cauchy Riemann conditions, and it comes from the same path independentness uh, property. Let us say that let f be defined from D to C. Okay, where D is some neighborhood in C or open set in C. Okay, now if f dash z not exist, we have written that. So I'm just giving you a proof of it. That how come this is the case? Uh, is a neighborhood in C, and f dash z naught exists because it is given that f is differentiable at z naught. It implies what? F dash z naught exist. So it implies what? It implies that this limit must exist. And let us take h. Let us take h is equal to h1 plus iota h2. Now, if h tends to 0, it implies h1 tends to 0 and h2 tends to 0. And if you remember, yesterday I took two specific paths. So today also we are going to take two specific paths. So in first path, let us say we put h2 equal to 0, and now let h1 tends to 0. So it implies that I'm approaching z naught along x-axis. Okay. So then f dash that equals to what? It is equal to limit h1 tends to 0, f of x naught plus h1 comma y naught minus f of x naught comma y naught divided by simply h1. And this we know this is equals to what? This is nothing but del f upon del x at z naught. Similarly, if I write that f dash z naught, and if I approach it along h2 tending to 0 and h1 equal to 0, it implies what? It implies limit h2 tends to 0, f of x naught comma y naught plus h2 minus f of, so sorry, f of x naught comma y naught divided by iota x2. Okay, so it is equals to what? It is equal to 1 upon iota, 1 upon iota, and then you have this del f upon del y at z naught. So if function is differentiable, then the limit must be path independent. Whatever path whichever path I take, the limit should be irrespective of that. So it implies that del f upon del x at z naught must be equal to 1 upon iota del f upon del y at z naught. And which implies what? Which implies that iota fx at x naught comma y naught must be equal to fy at x naught comma y naught. So these are Cauchy Riemann conditions written in capsule, a more sort of compact form. Again, you can bring out the Cauchy Riemann condition from here itself by putting f is equal to u plus iota v. We can again rewrite Cauchy Riemann conditions from here. One can rewrite the CR condition. I'm leaving this to you. You can do it on your own, I hope. Okay, all you need to do is equate imaginary by imaginary and real by real, and just place f is equal to u plus iota v here, and I think things will be easy. Okay. Okay. So now let us do a few things. And we've already seen a few things, like one of the things that we've seen, we have to really keep in mind. I'm writing because I'm revising the yesterday's lecture first. So one very important thing that I wrote yesterday was, if that is the converse statement, if Cauchy Riemann conditions hold, it does not imply necessarily, I would say, I would write it here, it does not necessarily imply, and let's say we would write a point. So let's say at z naught, all these Cauchy Riemann conditions are holding. So it does not necessarily imply that f is differentiable at z naught. Okay, so this is very important. Usually people make mistake here. They think that Cauchy Riemann conditions are true, then they think that function is differentiable at that particular point. This is certainly a false statement. And I gave you an example. Let us take another example today so that you'll be able to get this. So let's say today, let me take one example. Fz is equals to f simply x plus iota y here. And it is equals to what? It is equals to x cube minus y cube x cube plus y cube plus iota. And then you have this x cube plus y cube again, I think, divided by x square plus y square. All these things, if xy is not equal to 0, 0, and if xy is equal to 0, 0, then it is equal to 0. So if this is your fz, and if somebody asks how Cauchy Riemann conditions would be, so let us first try to find Cauchy Riemann conditions. So you know already that here u is equals to what? Ux comma y simply equals to x cube minus y cube, and let us try to find the Cauchy Riemann conditions specifically at a point, otherwise it will become a big problem. So let us find the validity of Cauchy Riemann conditions at 0 at first. So let us try to use let us try to find Cauchy Riemann conditions at 0, comma 0. So first let us find ux at 0, comma 0. So ux at 0, comma 0 will be equals to what? Limit h tends to 0, f of h, comma 0 minus f of 0, comma 0 divided by h. We already know that this is 0, so not a problem. And it implies that fx, this will be equals to what? It will be equals to h cube upon h square, h cube upon um, okay, h cube minus, oh, okay, let us do it. Let us do it, okay. Minus 0 whole cube divided by this entire thing. This will be, I think. Okay, let us try to do it in a different fashion. I think this is x cube plus y cube. No, this is x squared plus y. My bad, okay. Otherwise, the ux will become tending to infinity. Okay, so please correct it. This is x squared plus y squared. Here it is x squared plus y squared. Here it is also x squared plus y squared. So it will become h squared and divided by h also. And f00 is 0, so it will give you 1. And what would be ui at 0, comma 0? Ui at 0, comma 0 would be simply limit h tends to 0, and this will also this will be simply uh, f of 0, comma k minus f of 0, comma 0 divided by k, and this will also give you k cube upon k square into k, and which is again equals to what? 1. Okay. Okay, so please correct it. Actually, I wrote wrong initially. Because otherwise, if this would be x cube plus y cube, then this particular ux, this limit, when I'll be taking around 0, comma 0, it will be 1 over h, and that goes to infinity, and that would be a problem. So this is the question. Okay, actually I forgot to write the right one. This should be x squared plus y squared. Okay, so this is one of those functions where I'm going to show you that ux is equal to vx, ux is equal to vy, sorry, here clearly at 0, comma 0. And now let us find uy. Uy would be equal to what? It will be, I'm directly writing, it would be limit k tends to 0 minus k cube divided by k square into k, that is minus 1. So this is uy at 0, comma 0. And what is vx at 0, comma 0? So vx at 0, comma 0 is simply h cube upon h square into h. I think, I hope this definition you know by now. So this is equal to 1. So clearly, uy is equal to minus of vx at 0, comma 0. So both of so Cauchy Riemann conditions hold true. But is the function differentiable? Now question arises, is the function differentiable? Is the function fz differentiable? Differentiability of function means what? I will try to take differentiability at origin. So limit h tends to 0, f of 0 plus h minus f of 0 divided by h. Okay, now let us take two paths. One path I'm going to take around y is equal to x only. So along this line, we know that I can simply write any point to be equals to h comma h only. Okay, or simply h1 comma h1. So I'm taking this path. So at first I'm taking path limit h tends to 0, y is equal to x. So it is f of h1 plus iota h1 minus f of 0 divided by h1 plus iota h1. and what it will be like. So I know that if I'm placing this, what I'll be getting, let me see here. Okay, so it is equivalent to writing h1 comma h1. So if I'm writing h1 comma h1, u goes away, only this remains. Okay, I hope it is clear till now. So if this remains, so only v part remains. Okay, u goes away because if it is h1, so it will become 0, only this part will remain. So it will be iota 2h1 whole cube divided by 2h1 whole square. Okay, and then minus 0 upon h1 plus h1 plus iota h1, and it will be equals to what? It will be equals to iota simply h1 divided by h1 plus iota h1, and h1 certainly I'm not taking to be equal to 0. I'm taking h1 tending to 0 only. So so basically I'm talking of y is equal to x, it implies h1 tends to 0. Okay, so this limit h1 tends to 0, and here also limit h1 tends to 0. So limit is placed on h1, that is h1 is not completely 0, it is tending to 0. So I can write this is equal to iota plus 1 plus iota, and it is simply equals to what? It is equals to iota plus 1 divided by 2. Okay, you just multiply with 1 minus iota above and below, and you will get the same thing. So it's not a problem. Okay, now let us take another path. Let us take path along x-axis. So if I okay, so if I approach if I approach 0 along the x-axis, so along x-axis we know that your if I'm saying h is equal to h1 plus iota h2, then h2 should be equal to 0, and this h1 tends to 0, right? h1 tends to 0. So let us come back to the limit. So limit h1 tends to 0, f of h1 plus iota into 0 minus f of 0 divided by h1. So it will be equals to what? So at the place y, we are going to write 0. At place x, we are going to write h1. So it will give me h1 plus iota h1. So h1 plus iota h1 divided by h1. Limit h1 tends to 0. It will give you what? It will give you a result 1 plus iota. So clearly, the function is non-differentiable because we have taken two different paths and we are getting two different limits. Non-differentiable at z equal to 0, since the limit turns out to be path dependent. So yesterday also we took a few one example, and we tried to establish that the necessity for the Cauchy Riemann conditions, necessity for the differentiability is uh, Cauchy Riemann condition. It is not the condition for sufficiency. That is, if Cauchy Riemann conditions are met, we cannot say at a point, if we are saying that Cauchy Riemann conditions are met, it does not imply that at those points your function would be differentiable. Another example you can take. Let us take another example. So let's say fz is equals to what? Fz is equal to, let us say, if I remember, it is z raised to power 5 divided by mod z whole power 4. Z not equal to 0. And if z is equal to 0, then it is equal to 0. Okay, and just try to find here also. I mean, this is easy thing to do. I mean, I'm leaving it up to you if you want to really see. This is one example. Okay, let me do. So now I'll use the different condition, other condition that I wrote for Cauchy Riemann conditions. So Cauchy Riemann conditions can be encapsulated in this form also. That is iota fx at x naught comma y naught should be equal to what? It should be equal to fy at x naught comma 1. Okay, x naught comma 1. Sorry. Okay, so first find fx. Let's say it's 0 comma 0 only I'm taking. Okay, so it is equal to limit h tends to 0 f of h comma 0 minus f of 0 comma 0 divided by simply h. So it will be equals to what? It will be equals to h raised to power 5 divided by mod h whole power 4 into h. And if h is on the positive side, okay, if h is on the positive side, um, we are taking h to be greater than 0 only, okay? So h tends to 0 and h is greater than 0. This is what we are taking. So what we'll get from here, we'll simply get 1, okay? And what about fy? So let us try to find fy at 0 comma 0. It is equals to what? Okay, so whether we take positive or negative, I mean positive side or negative side, h always remains to be positive. So anyway, it is going to be equals to 1 only. Okay, so this is what I wanted to convey. And what would be fy at 0 comma 0? Limit h tends to 0 f of 0 comma h minus f of 0 comma 0 divided by h. And it will be equals to what? It will be equals to limit h tends to 0 f of 0 plus h. F of 0 plus h is what? It is simply um, instead of z, I will write here iota h whole raised to power 5 divided by iota h mod whole raised to power 4 into iota h. So I'll get here is I'll simply get iota because iota raised to power 4 is 1 and 1 iota raised to power 5 would be iota here h raised to power 5 divided by h raised to power 4 mod into h and then there should be a iota as well. Okay, and then again, have I made a mistake somewhere or what? So this was fine. 0 comma h minus f of 0 comma 0 divided by h. Why this iota has appeared? So sorry. Okay, z will be equals to this. So z is equal to what? Z is equal to 0 plus iota h. Okay, but here it was h only, right? So I don't have to use iota here. This is fine. So here I'll get simply iota. Okay, so now clearly iota fx at 0 comma 0 is simply fy at 0 comma 0. So Cauchy Riemann conditions are met at 0 comma 0. Okay, hold good at 0 comma 0. Please remember, okay, this is h only. This is not iota h here. My mistake. Okay, z is equal to 0 plus iota h. So instead of z, we have to write 0 plus iota h or simply 0 comma h minus h 0 0 and upon h. So you have to pay attention. Otherwise, we'll make a mistake here. So Cauchy Riemann conditions hold good at 0 comma 0. Now question arises, is the function differentiable? Is the function differentiable? So had the function been differentiable, it implies what? Limit x tends to 0 f of h minus f of 0 divided by h. It should exist. And what does it mean? It means h raised to power 5 upon modulus of h raised to power 4 into h. Or in other words, it is equals to h raised to power 4 divided by mod h raised to power 4. Let us take a path h is equal to, let's say, del e raised to power iota theta. And if h tends to 0, it implies del tends to 0. So all these things converts to writing limit del tends to 0, del raised to power 4, e raised to power iota 4 theta divided by del mod whole raised to power 4 e raised to power iota 4 theta mod. This is 1. So this, and del is positive, so this will become 1 only. So e raised to power iota 4 theta. Clearly, this limit turns out to be path dependent. Since it is a path dependent limit, so therefore function is non-differentiable at 0, 0. Okay, so clearly one can see that this particular function is non-differentiable at 0, 0. However, what happened was, however, we can say that at 0, 0, Cauchy Riemann conditions are true, but it is non-differentiable at 0, 0. So you have to remember this time and again. I'm focusing another example that proves the same, and I'm leaving this as a homework to you. Try to take this example and find Cauchy Riemann conditions and find the differentiability also. Fz is equal to imaginary part z square upon mod z whole square if z is not equal to 0, and if z is equal to 0, then it is simply equals to 0. Okay, let us say this particular function I'm giving you as a homework. Try to do it. Try to do this as a homework. Okay. So again, yesterday only I told you that sufficient conditions would be not only the holding of Cauchy Riemann conditions, but their continuity should also be there. So this is what I wrote yesterday, and for revision sake, I'm doing it. That if f is defined from D to C, and D is an open set contained in C, D is an open set contained in C, and um, let us say we are talking of point Z naught belongs to D. Now, and let us define that Fz is equal to what? Fz is equal to U plus iota V. Then, what are the conditions? The first condition was that Ux, that is the first order partial derivatives, Ux, Vx, Vy, and Uy. All these first order partial derivatives must exist at each point, in the neighborhood of, please remember, okay, in the neighborhood of point Z0. Not only they should exist in the neighborhood of Z0. And why neighborhood is compulsion? Because you have to find the continuity also. So Ux, Vy, Uy, and Vx, these first order partial derivatives should exist at each point in the neighborhood of Z0, and they must be continuous. They must be continuous at Z0. Okay. If this is the case, and then Cauchy Riemann conditions are valid. Cauchy Riemann conditions are valid at Z0. Then this forms a sufficient condition. Then it implies that f is differentiable at Z. Okay. This is very important. You have to remember this. Okay. Now, let us take so all these things are nothing but the revision of yesterday's lecture only. So I hope now you know everything regards yesterday's lecture. Yesterday's lecture was very important. Please remember Cauchy Riemann conditions. One question you can expect each year in any of your exam, like the exams that you're preparing, CUET, NET GATE, or any PhD entrance for that matter. So let us consider one example, that is Fz is equal to U plus iota V, and let us take U is equal to X square Y square, and let us take V is equal to again this is a problem. V is equals to simply 2x square Y square. That's good now. So we have taken u is equal to x square y square and v is equal to 2x square y square. And now clearly we can say that u and v are both continuous. And their partial derivatives exist. Clearly, you can see their partial derivatives exist. Partial derivative exist. So ux is equal to what? Ux is equal to simply 2xy. And uy is equal to what? It is vy is equal to what? Sorry, it is 4x square y. What is uy? Uy is simply 2x square y. And what is vx? Vx is 4x y square. Okay. So if I write Cauchy Riemann condition, it implies ux should be equal to vy, which is writing 2xy square is equal to 4x square y, and uy is equal to minus vx is equivalent to writing 2x square y is equal to minus 4xy square, which implies what? Which implies if I write the first one, this equation, it is equals to, if I take xy common out, it will be equals to y minus 2x equal to 0. And if I take the second condition, then it implies xy into x plus 2y must be equal to 0. Okay. So both these conditions clearly show that, I'm writing, it implies what? CR conditions hold only along the line, y is along the lines x equal to 0 and y equal to 0. Okay. Otherwise, it will not be both 0 together. So here the condition for being together is y is equal to 2x, but here the condition is x equal to minus 2y. And so you can find on your own that the Cauchy Riemann condition will hold only along x equal to 0 or y equal to 0. That is along y-axis and x-axis respectively. This I'm leaving up to you. You can do it on your own. Okay. So now Cauchy Riemann conditions are holding true only for x equal to 0 and y equal to 0. Further, we also know that both of these derivatives for first order partial derivatives are also continuous. Okay, so they are continuous on entire complex plane, in fact, but they are continuous also on x equal to 0 and y equal to 0. Cauchy Riemann conditions are holding true. It implies what? F is differentiable only on the points x equal to 0 and y equal to 0. That is, f is differentiable only along y-axis and x-axis. Okay, I hope it is clear. So f is differentiable only along x-axis and y-axis. So now question arises whether this function is analytic or not. So clearly this function is not analytic. In fact, this function is nowhere analytic. Why? For function to be analytic at a point, first thing is function must be differentiable at that point. Not only this, it must be differentiable in the neighborhood containing that point. So I know my function is only differentiable on x-axis and y-axis. Okay, now let's say if I take a point here, on y-axis, so just not this point, it should be differentiable in some neighborhood containing this point. And I know that function is not differentiable in this region. So it is only differentiable at that particular point on y-axis. It is not differentiable in any neighborhood containing that particular point. So clearly, I can say that my function is nowhere analytic in C. So this you have to remember. I mean, every time analyticity comes, the extra condition is If I'm talking of analyticity at a point, then I must be sure that function is differentiable at that point, and also at every point uh, in some neighborhood containing that set knot. Okay, so for example, if I'm saying that my function is different analytic at this point, then it must be differentiable at this point and at every point in some neighborhood of this particular point. Okay, only then I can say analyticity. Otherwise, I cannot claim analyticity. This is very important. Please remember. Another important result I'm writing, and we'll be discussing this result in the next class, that if f is a constant, if f is a constant in some domain D, okay, if f is a constant in some domain D and we want to find the derivative, then f dash z must be equal to 0. Please remember it should be domain. Domain means here I'm trying to write open and connected set. Okay. And another thing, if f dash z is equal to 0 in domain D, then f must be a constant. And please remember this condition is not superfluous. I'm not writing just because it's coming in my mind. It should, f must be a constant in some domain D, that it must be constant in some connected and open set. If the set is not connected, then this may not be true also. Okay, so if f is a constant in some domain D, then the derivative must be equal to 0. And if derivative of a function is 0 in some domain D, then f is a constant. So this, please remember, I'm just writing it here. Okay, the condition that f must be defined on connected set is not, cannot be relaxed or is not superfluous. Okay, so you have to remember this. It's not that it is I'm just writing it for the sake of writing. No, it is really the case, because let us take example. Let us take one example and let us try to understand. Let us take an example, f defined from D to C, and here D is not connected. And let us take example like this. Let me write fz is equal to uh, fz is equals to what? It is equal to 0 if mod z is less than 1, and if mod z is greater than 3, it is equals to, let's say, iota. Okay. Okay, this is the fz is equal to this. And we know that constant function is analytic. So fz clearly belongs to set of analytic functions. That's not a problem on the given domain. And the domain is not connected, that is clear. Okay. Now in this particular domain, I know that my function's derivative must be equal to what? It would be 0 for all z belongs to D. But is function constant? Clearly not. Because for function to be constant, it should be having the same value throughout D. But f is non-constant in D. So you have to remember this, that if f is constant in some domain D, where domain D I'm referring to connected set plus open set. So you have to have a connected set, and then if f dash z is equal to 0, then if we take the derivative, then f dash z is equal to 0. Or if f dash z is equal to 0 in D, then f must be a constant. We will start our lecture from this particular point only in the next class. Till then, take care.